Hello friends, I welcome you to my lecture on properties of homogeneous system. We shall try to find the all solutions of the homogeneous system given by x dot equal to Ax, where as you know x is represents the vector valued function with having n components x1 t, x2 t and so on xn and A is the matrix Aij, where I runs from 1 to n and j runs from 1 to n. Such a system we know is a homogeneous system of first order linear differential equations. Now, first we show that the constant times of a solution and the sum of two solutions are again solution of this homogeneous system 1. Let us say xt and yt be any two solutions of the homogeneous system 1, then first we show that cxt is a solution for any constant c, and second is xt plus yt is again a solution. Now, we shall make use of the lemma here, let A be an n by n matrix for any vectors x and y and constant c, A into Cx is equal to C times Ax and A into x plus y is equal to Ax plus Ay. These are the properties of matrices and they are very simple to prove. So, we shall make use of this lemma. Now, you can see that dx by dt is equal to this x dot equal to Ax gives dx by dt is equal to Ax. So, when you want to prove that Cxt is a solution, you need to show that d over dt of Cxt is equal to A up into Cxt. Okay. So, d over dt of Cxt will be C times d over dx over dt, which will be C times Ax, and C times Ax is equal to A times Cx. So, we will get d over dt of Cxt equal to A into A Cxt, and therefore, Cxt is a solution of the differential equation x dot equal to Ax. Now, again if you want to show that xt plus yt is a solution, then if xt is a solution, then x dot equal to Ax and yt is a solution means dy over dt is equal to Ay. So, if you want to prove that xt plus yt is a solution, then d over dt of xt plus yt will be dxt over dt plus dyt over dt, which will be equal to Ax plus Ay, and Ax plus Ay you can see in lemma 2, lemma b part, Ax plus Ay is equal to A into x plus y. So, d over dt of x plus y equal to A into x plus y, and therefore, if xt and yt are solutions of the homogeneous system x dot equal to X, then xt plus yt is also a solution of the homogeneous system. Now, let us look at a corollary of this theorem 1. So, any linear combination of solutions of 1 is again a solution of 1, that is if x1t, x2t and so on xjt are j solutions of equation 1, then c1 x1t plus c2 x2t and so on cj xjt is again a solution of the equation 1 for any choice of constant c1, c2, cj. So, this follows from the theorem 1, because d over dt of c1 x1t plus and so on cj xjt will be equal to c1 times dx1 over dt plus c2 times dx2 over dt plus and so on cj times dxj over dt. Now, which will be equal to c1 times a x1t plus c2 times a x2t and so on cj times a xjt, which will be equal to a operating on a into c1 x1t plus c2 x2t and so on cj xjt. So, if x1t and x2t and so on xjt are solutions of equation 1, then their linear combination is also a solution of equation 1. Now, let us consider, let us take an example here. Let us consider the system of equations dx1 by dt equal to x2, dx2 by dt equal to minus 4x1. So, this you can see is a homogeneous system of two differential equations of first order. So, this can be written in the vector in the form of the matrix equation dx by dt equal to, now here the coefficient of x1 is 0. So, we have 0 here, coefficient of x2 is 1, and in the second equation coefficient of x1 is minus 4, coefficient of x2 is 0. So, we have the coefficient matrix A as 0 1 minus 4 0 x is x1 x2. So, we can write the given system of two differential equations in a convenient form, which is dx by dt equal to Ax. A is the matrix 0 1 minus 4 0. Now, this system of equations is obtained from the second order differential equation with constant coefficients d square by over dt square plus 4 by equal to 0. To see this, what we do is, let us put x1 equal to y, let x1 equal to y and x2 equal to dy over dt. Then dx2 over dt will be equal to d square by over dt square, and dx1 over dt will be equal to dy by dt, which will be equal to x2. Okay. So, thus we have thus we get dx1 by dt equal to x2. This is one equation. Second equation, dx2 by dt is equal to d square by dt square, and we have the second order equation as d square by dt square plus 4y equal to 0. So, this is equal to minus 4y, minus 4y means minus 4x1. So, you can see we get two equations, dx1 by dt equal to x2 and dx2 by dt equal to minus 4x1. So, now in order to find the general solution of this system of differential equations, what we notice is as d square by over dt square plus 4y equal to 0. This is a second order linear differential equation with constant coefficients. So, we know how to find its solution. The auxiliary equation is m square plus 4 equal to 0, which gives us two values of m plus minus 2i, and therefore, y is equal to some constant a times cos 2t plus some constant b times sin 2t, and therefore, cos 2t and sin 2t are two solutions of this differential equations. Now, let us say by 1 t is equal to cos 2t and by 2 t is equal to sin 2t. Okay. Then now we are looking for the solution of the homogeneous system of equations dx1 by dt equal to x2, dx2 by dt equal to minus 4x1. So, xt is equal to x1t, x2t will be equal to some constant c1 times. Now, x1t, let us take the x1t to be cos 2t. So, cos 2t and then its derivative, because x2 is equal to dx1 by dt. So, we get minus 2 sin 2t, derivative of cos 2t is minus 2 times sin 2t plus c2 times. Now, this time we take sin x1t to be sin 2t, and then derivative of dx x1 gives x2, this x2. So, we get derivative sin 2t as 2 cos 2t, and this gives you c1 cos 2t plus c2 sin 2t minus 2 c1 sin 2t plus 2 c2 cos 2t. So this gives us xt equal to this is the general solution of the given system of equations for any choice of constants C1 and C2. You can see xt is equal to minus C1 times cos 2t plus C2 times sin 2t, then minus 2 C1 sin 2t plus 2 C2 cos 2t. This is a solution of the given system for any choice of constants C1 and C2. Now our next step is to determine the number of solutions we must find before we can generate all solutions of the system of equations x dot equal to Ax. For this we will have to use a linear algebra. So let us begin with the definition of a vector space. A vector space is also called a linear space. So it is a set B on which we define two operations. One is denoted by plus, the other is denoted by dot. The plus operation is known as vector addition and the dot is known as scalar multiplication. So with respect to the vector addition operation, there must be the following conditions must be satisfied. First is closure. If u and b are any two vectors in B, then their sum u plus b must be an element of V. Then commutative law, u plus b is equal to b plus u for all u b belonging to B. Associative law, u plus b plus w is equal to u plus b plus w for all u b w belong to B. Additive identity, there exists an element denoted by 0 in B such that 0 plus b is equal to b plus 0 equal to b for all b belonging to B. Additive inverse, for each vector v in B, there are the equations v plus x equal to 0 and x plus b equal to 0 have a solution x in B, which is called the additive inverse of B, and we denote it by minus b. With respect to the scalar multiplication operation, there must hold the following conditions. Closure, if B is an element of B and C be a scalar, then C into B belongs to B. Distributive law, C dot u plus b equal to C dot u plus C dot b for all scalar C and any vectors u b belong to B, and C plus D dot b equal to C dot b plus D dot b for all scalar C D and B belongs to B. The associative law, C dot D dot b equal to C D dot b for all scalars C and D and vectors B belong to B. And then finally unitary law, 1 into B equal to B for all B belonging to B. Now you can see that if B denotes the set of all solutions of the homogeneous system x dot equal to Ax, then B is a vector space because first of all we have already seen that if u and b are any two solutions of x dot equal to Ax, then their vector addition, that is x u plus b also is an element of B, that is u plus b is also a solution of B. So B is closed with respect to the vector addition operation. Then if you take any two solutions u and b belonging to B, then the commutative law u plus b equal to B plus u is clear. Associative law, u plus b plus d b plus w, u plus b plus w for all u b w belong to B. If u b w are solutions of the equation x dot equal to X, then this associative law is also clear. Now additive identity, there exists an element denoted by zeros in B such that b 0 plus b equal to b plus 0 plus equal to b for all b belong to B. So here the additive identity in the case of B, which is the space of all solutions of the system x dot equal to X, is the 0 solution, that is xt equal to 0 0 0 0. All the components of the solution xt are zeros. So such a solution obviously satisfies the differential equation dx by dt equal to Ax. If you put x equal to 0, then x dot is 0 because all derivatives of all components are zeros, and is equal to a times x, so a times 0 is 0. So 0 solution obviously satisfies the homogeneous system. So that 0 solution belongs to V and plays the role of the additive identity here. If you add 0 solution to any solution V belonging to B, then you get B plus 0 equal to B. So additive identity exists in the space B, and moreover if B is any solution, then minus B is also a solution, because we already have seen that if B is a solution, then C times B is a solution of the homogeneous system x dot equal to x. So, take C equal to minus 1. So, then if B is a solution, then minus B is also a solution, and that minus B plays the role of the additive inverse, because B plus minus B is equal to 0 solution, and minus B plus B is also is equal to 0, which is the additive identity. So, additive inverse exists in the space B, and we have already seen that if x is a if B is a solution of the homogeneous system, then C times B is a solution of the homogeneous system. So, closure property holds. Then distributive law, C times C dot u plus B equal to C dot u plus C dot B clearly holds if u and B are any solutions of the system x dot equal to Ax and C is a scalar. And if you take any two scalars C and D and B to be any solution of the x dot equal to Ax, then C plus D dot B equal to C dot B plus D dot B is also true, and similarly associative law is true. Unitary law 1 dot B equal to 1 also clearly holds. So, B, if B denotes the space of all solutions of the homogeneous system x dot equal to X, then B is a vector space. Now, let B be the set of all vector valued solutions x t equal to x1 t, x2 t, xn t. This is transpose. So, that means this is a row vector. When we take transpose, it becomes a column vector. So, x t is a solution of the space the equation x dot equal to Ax, and B is the set of all such vector valued solutions of the equation x dot equal to Ax, where A is this n by n matrix vector differential equation. Now, then B is a vector space, as I said already, under the usual operations of vector addition and scalar multiplication. Now, in order to solve the homogeneous system of homogeneous linear system of equations x dot equal to Ax, we shall need the following existence uniqueness theorem. There exists one and only one solution of the initial value problem x dot equal to Ax, x t naught equal to x naught, where x t naught is equal to x1 naught, x2 naught, the column vector x1 naught, x2 naught, xn naught, t, t is the transpose. So, when we take the transpose of the row vector, we get the column vector, and moreover this solution exists for minus infinity less than t less than infinity, the over all values, real values of t. So, this t, do not confuse this t with this t, okay. This t is the independent variable, okay, here. Now, so we shall need this theorem, and in existence uniqueness theorem you have already done for the equation dx by dt equal to f tx. So, the proof of this theorem follows along similar lines. So, right now we will make use of this theorem. If x t is a non-trivial solution, now let us look at this remark. If x t is a non-trivial solution of the initial value problem, this is the initial value problem x dot equal to Ax, where x at t naught is given by the vector x naught. So, if x t is a non-trivial solution of this initial value problem, then x t cannot be 0 for any value of t, because if x t is equal to 0 for some value of t, say t equal to t star, then x t must be identically 0, because the trivial solution also satisfies the differential equation x dot equal to Ax. So, if the trivial solution and the then if x t star is equal to 0, then the trivial solution and x t solution will coincide at t equal to t star, and so by the uniqueness of the solution it will follow that x t is equal to 0 for all t. So, if x t is a non-trivial solution, then x t must be not equal to 0 for any value of t. Now, we know that we have already seen that the space B of all solutions of 1 is a vector space. So, now what we are going to do is now the question is that how many solutions linearly independent solutions of B of the equation x dot equal to Ax we must find, so that we can write the general solution of x dot equal to X. That question is answered by this theorem. This theorem tells us that the dimension of the space B of all solutions of the homogeneous linear system of differential equations 1 is n. Okay. So, this theorem tells us that if we can find n linearly independent solutions of the homogeneous linear system x dot equal to Ax, then we can write the general solution. The general solution will be a linear combination of those n linearly independent solutions. So, this theorem is very important. Let us prove this theorem. So, what we do is in order to prove this theorem, we need to show that the vector space B has a basis which has got n elements. Okay. So, what we do is, let us say, let phi j t j equal to 1, 2 and so on up to n, okay, be the solution of the initial value problem x dot dx by dt equal to Ax, x0 is equal to Ej where Ej denotes the vector column vector 0 0 0 and so on 1 occurs in the jth row and so on up to 0. Okay. Now, from the existence and uniqueness theorem, phi j t exists for all t and is unique. Okay. So, let phi j t be the solution, phi j t where j runs from 1 to and so on up to n, be the solution of the initial value problem. This is the initial value problem. You can see dx by dt equal to Ax, the value of x at 0 is the vector Ej, okay, where 1 occurs in the jth row. For example, if you write for j equal to 1, then phi 1 t will be solution of dx by dt equal to x, and x at 0 will be 1, then 0 0 0 and so on up to 0. So, we shall actually show that these n functions phi j t form a basis for the solution for the vector space B. Okay. So, if we can show that this n functions phi j t form a basis for the vector space B, then the dimension of B will be equal to n. Okay. So, let us from the existence and uniqueness theorem, it follows that phi j t exists and is unique. Now, what we do is first we show that these n functions phi j t are linearly independent. First we show that phi j t j equal to 1, 2 and so on up to n, these n functions are linearly independent. Okay. So, for this what we will do, let us write the equation C1 phi 1 t plus C2 phi 2 t and so on Cn phi n t equal to 0, where C1, C2, Cn are constants. So, if we want to show that phi 1 t, phi 2 t and so on phi n t are linearly independent, then we must show that C1, C2, Cn are all zeros. So, we must show that C1, C2, Cn are all zeros. Now, since this equation C1 phi 1 t plus C2 phi 2 t and so on Cn phi n t is equal to 0 is valid for all t, okay, let us put t equal to 0 in this equation. So, putting t equal to 0, we get C1 510 plus C2 520 and so on Cn phi n 0. Okay. Now, phi 1 0 is equal to E1. Okay. So, we get C1 E1, then C2 E2 and so on Cn En equal to 0. Now, we know that the vectors E1, E2 and so on En are linearly independent vectors in Rn. Okay. So, C1 must be equal to 0, C2 must be equal to 0 and so on, Cn must be equal to 0, and thus phi 1 t, phi 2 t and so on phi n t are linearly independent. So, thus the n functions phi 1 t, phi 2 t and so on phi n t are linearly independent. Now, we show that any x t belonging to B is the space of all solutions of the homogeneous system x dot equal to x. Any x t belonging to B can be written as a linear combination of phi 1 t, phi 2 t and so on phi n t. So, that will mean that the span of the vectors phi 1 2, phi 2 t and so on phi n t is equal to B. And since we have already shown the linear independence of phi 1 t, phi 2 t and so on phi n t, it will follow that they form a basis for the vector space B. Now, what we do is, let us say that x 0 is equal to C1, C2 and so on Cn. X t is any vector belonging to the vector space B. Okay. We want to show that x t is a linear combination of phi 1 t, phi 2 t and so on phi n t. So, let us assume that at x t function at t equal to 0 is given by this column vector C1, C2, Cn. Then let us construct the function phi t equal to C1 phi 1 t, C2 phi 2 t and so on Cn phi n t. Now, since phi 1 t, phi 2 t and so on phi n t is a solution of x dot equal to Ax, okay, then their linear combination C1 phi 1 t plus C2 phi 2 t and so on Cn phi n t will also be a solution of the equation vector differential equation x dot equal to Ax. Now, what we notice is that let us put 0 in this. So, then phi t is clearly a solution of x dot equal to Ax. Now, phi 0 is equal to C1 phi 1 0 plus C2 phi 2 0 and so on Cn phi n 0, which is equal to C1 E1 plus C2 E2 and so on Cn En. which is equal to C1 times 1 0 0, C2 times 0 1 0 0 and so on, Cn times 0 0 and so on 0 1. This will give us C1, C2 and so on Cn, which is equal to x0 by our assumption. So, now what do we notice? We see that phi t is a solution of x dot equal to Ax, okay. Xt is also a solution of x dot equal to x, and phi 0 and x 0 are same. Phi 0 matches with x at t equal to 0. So, this means that by the existence and uniqueness theorem, it follows that the solution of the equation x dot equal to Ax must be unique. Therefore, phi t must be same as xt. So, by existence uniqueness theorem, x phi t must be equal to xt. Xt and phi t must be identical. And thus, replacing xt by phi t by xt here, xt is equal to C1 phi 1 t plus C2 phi 2 t and so on Cn phi n t. So, the functions n functions phi 1 t, phi 2 t and so on phi n t generate the whole space B, that is a linear combination of those n functions gives us any vector x t belonging to B. So, hence phi 1 t, phi 2 t is and so on phi n t form a basis of x dot equal to Ax, okay, and which means that dimension of B is equal to n. So, dimension of the vector space B is equal to n. So, this means that in order to write the general solution of the vector space B of the vector differential equation x dot equal to x, we need to find n linearly independent solutions of the vector differential equation x dot equal to Ax. Now, our next theorem will tell us how to check the linear independence of the n solutions of the differential equation x dot equal to Ax. So, let us go to that theorem. Here we have said that since dimension of B is equal to n, we need to find n linearly independent solutions of the system 1, that is x dot equal to x, in order to write the general solution of the equation x dot equal to x. So, the following theorem yields us a test for the linear independence of solutions of 1. It turns out that the n solutions x1, x2, xn of 1 are linearly independent if and only if their values x1 at t naught, x2 at t naught and xn at t naught at an appropriate t naught are linearly independent vectors in Rn. So, you can see the to check the linear independence of the n solutions, it is very easy. What you do, you choose a suitable t naught, a convenient t naught, and then evaluate the values of the n functions x1, x2, xn at t equal to t naught and check for the linear independence of the n vectors x1 t naught, x2 t naught, xn t naught in Rn. So, let us look at the theorem. This theorem says that if x1, x2, xk be any k solutions of the vector differential equation x dot equal to Ax, then select a convenient t naught. It follows that x1, x2, xk are linearly independent solutions if and only if x1 t naught, x2 t naught and so on xk t naught are linearly independent vectors in Rn. So, let us assume that x1 t naught, x2 t naught, and so on xk t naught be linearly independent vectors in Rn. Okay. So, let us assume that x1 t naught, x2 t naught and so on xk t naught be linearly independent vectors in Rn. Then we have to prove that x1, x2, xk are linearly independent solutions. So, we shall prove it by a contradiction method. So, assume that x1, x2 and so on xk be linearly dependent solutions. Then why the definition of linear dependence of vectors? Then there exist scalars C1, C2 and so on Ck not all 0 such that C1 x1 plus C2 x2 and so on Ck xk is equal to 0. This equation holds at for all t. Okay. C1, that is C1 x1 t, x1 is a function of t, x2 is a function of t. So, C1 x1 t, C2 x2 t and so on Ck xk t is equal to 0. Now, let us put t is equal to t naught in this equation. Then we get C1 x1 t naught plus C2 x2 t naught and so on Ck xk t naught equal to 0, okay, which implies that the k vectors x1 t naught, x2 t naught and so on xk t naught are linearly dependent vectors in Rn. So, which is a contradiction, because we have assumed that x1 t naught, x2 t naught, xk t naught are linearly independent. So, which is a contradiction. And thus, it follows that if x1 t naught, x2 t naught and so on xk t naught are linearly independent vectors in Rn, then the n functions x1 t, x2 t and so on the k functions x1 t, x2 t and so on xk t are linearly independent solutions of the vector differential equation x dot equal to x. Now, let us prove the converse. So, conversely, let us assume that x1, x2 and so on xk be linearly independent solutions of the vector differential equation x dot equal to Ax. We have to prove that the k vectors x1 t naught, x2 t naught, xk t naught are linearly independent. So, let us assume that the k vectors x1 t naught, x2 t naught and so on xk t naught be linearly dependent. Okay. So, again we shall have to arrive at a contradiction in order to prove the result. So, by the linear definition of linear dependence, there exists scalars C1, C2 and so on Ck not all 0 such that C1 times 1 T naught plus C2 times x2 T naught and so on Ck times xk T naught is equal to 0. Okay. Now, what we do is so with this choice of constant C1, C2, Ck, with this choice of let us construct the function phi t equal to C1 x1 t, C2 x2 t and so on Ck xk t. Okay. Then since x1 t, x2 t, xk t are solutions of the vector differential equation x dot equal to x, okay, it follows that phi t is a solution of x dot equal to x. So, then phi t is a solution of x dot equal to x. Moreover, phi t naught is equal to C1 x1 t naught, C2 x2 t naught plus Ck xk t naught, okay, is equal to 0. You see C1 x1 t naught, C2 x2 t naught, Ck xk t naught is equal to 0. So, phi t naught is equal to 0. So, what happens is that phi t is a solution of the differential equation x dot equal to Ax such that phi t naught is equal to 0, and this means that phi t must be 0 for all values of t. Okay. So, by existence uniqueness theorem, phi t and the trivial solution must be the same. So, phi t is equal to 0 for all t, okay, and which implies that C1 x1 t plus C2 x2 t and so on Ck xk t is equal to 0 for all t, and this tells us that the k functions x1 t, x2 t and so on xk t are linearly dependent, okay, and so we get a contradiction. So, this proves the theorem. So, the k functions x1 t, x2 t, xk t are linearly independent if and only if at an appropriate t naught the k vectors x1 t naught, x2 t naught and so on xk t naught are linearly independent. Now, let us consider the system of differential equations dx1 by dt equal to x2 and dx2 by dt equal to minus x1 minus 2x2. You can see we can write this in the vector differential equation form dx by dt equal to, now coefficient of x1 is 0 here. So, 0, coefficient of x2 is 1 and then here coefficient of x1 is minus 1, coefficient of x2 is minus 2. So, the matrix A is 0 1 minus 1 minus 2. Now, this system of equations has been obtained from the single second order differential equation d square by over dt square plus 2 dy over dt plus y equal to 0. You can see here if you take x1 equal to y, x2 equal to dy by dt, then what you get dx1 by dt is equal to dy by dt which is equal to x2 and dx2 by dt will be equal to d square by dt square which is equal to minus 2 dy by dt is x2 minus y. So, minus x1. So, you can see we have dx1 by dt equal to x2 dx2 by dt is equal to minus x1 minus 2x2. So, this system of differential equations has been obtained from this single second order differential equation d square y over dt square plus 2 dy by dt plus y equal to 0. Now, let us find the solution of this differential equation, system of differential equation. So, what we will do is we will find first the solution of this second order differential equation, which is a differential equation of second order with constant coefficients. So, what we will do is we can write the auxiliary equation here. We have m square plus 2m plus 1 equal to 0, which gives us m is equal to minus 1 minus 1. So, two values of m are same, and therefore, the solution, general solution of this second order differential equation will be by t equal to c1 plus c2 t into e raised to the power minus t. So, we can take two solutions of this second order differential equation as by 1 t equal to e to the power minus t and by 2 t is equal to t into e raised to the power minus t. Okay. Now, we can get solutions of, we can get two solutions, x1 t is equal to e to the power minus t and then minus e raised to the power minus t, and x2 t equal to t e to the power minus t, and then we differentiate t e to the power minus t d over dt of t e to the power minus t is equal to a derivative of t is 1. So, we get e to the power minus t, and then we get t times minus e raised to the power minus t. So, we get 1 minus t into e raised to the power minus t. So, we get 1 minus t into e raised to the power minus 2 minus t. Okay. Now, we can see the linear independence of these two solutions of the differential equation x dot equal to ax. Okay. What we do is we choose a suitable value of t. Let us take t equal to 0. So, then x1 0 is equal to 1 minus 1, okay. x2 0 is equal to 0, and here we will get 1. Okay. So, 1 minus 1 and 0 1, we have to show that these two are linearly independent. So, C1 times 1 minus 1 plus C2 times 0 1 equal to 0 gives us what you have C1 plus 0, so C1, and then here minus C1 plus C2. So, minus C1 plus C2 equal to 0. 0 is 0 0. Okay. So, this implies C1 is equal to 0 and C2 equal to C1. Since C1 is 0, C2 is also 0. So, we get C1 and C2 both are zeros, and hence x1 0 and x2 0. The two vectors are linearly independent in R2. So, by the theorem which we have just now done, if k vectors x1, x2, xk at t equal to t naught are linearly independent, then the k functions x1, x2, xk are linearly independent. So, x1 t, the two solutions x1 t, x2 t are linearly independent. And so, we can write the general solution of the given system. General solution is x t equal to C1 times x1 t plus C2 times x2 t, which is equal to C1 times e raised to the power minus t minus e raised to the power minus t plus C2 times t e raised to the power minus t and 1 minus t e raised to the power minus t. So, this gives you C1 plus C2 t into e raised to the power minus t, and then we will get here what C2 minus C1 minus C2 t into e raised to the power minus t. So, this is also a solution of the equation x dot equal to Ax for all values of t. So, this is a general solution of the given system of equations. Now, here what I have done is I have taken the initial value problem, the same vector differential equation I have taken as in the case of example 2, dx by dt equal to 0 1 minus 1 2. Only what I have done is I have given the initial condition, that is at t equal to 0, x is 1 1 vector. Okay. So, we know that x t is equal to we have found x t equal to okay, C1 plus C2 t into e raised to the power minus t, C1 plus C2 t into e raised to the power minus t, and then C2 minus C1 minus C2 t into e raised to the power minus t. So, this general solution of the this equation x dot equal to x. If we want the solution of this initial value problem, then let us put t equal to 0. So, x 0 is equal to what I get, this is 0, this is 1. So, we get C1 and here we get C2 minus C1. Okay. Now, x 0 has to be equal to 1 1. So, what I get, C1 is equal to 1 and C2 minus C1 equal to 1 implies C2 equal to 2. So, we get x t equal to C1 is 1, C2 is 2. So, 1 plus 2 t e raised to the power minus t, and then here C2 is 2, C1 is 1. So, 2 minus 1 is 1, 1 minus 2 t into e raised to the power minus t. So, this is how we get the particular solution of the initial value problem by satisfying the condition x 0 equal to 1 1 in the general solution. So, this is how we solve this homogeneous system of linear differential equations. Now, in our next lecture we shall discuss the method of eigenvalues and eigenvectors by which we can find the general solution of the homogeneous system of linear system of differential equations. Thank you very much for your attention.